Assalamu alaikum, dear students. Welcome back to another video lesson of chapter number 2. Last time we were talking about torque. Let me give you a quick recap of what we've studied last time. So we said that if we have an object, a beam, let's say, if a force is acting at a certain distance to the axis of rotation, then it produces a torque. So torque is equal to force times distance. Once again, if we have angles, we'll say times sine theta here. Clearly, torque, you could say it is a quantity that measures the ability of a force, all right, that causes or rotate an object around some axis of rotation, you could say. Okay, we also said that this torque is equal to, or the equation of torque is equal to force times distance times sine theta. We know that based on this equation, torque is directly proportional with the force. It is also directly proportional with the distance, and also you could say torque depends on or directly proportional to the angle theta as well, as long as you could say theta is between 0 to 90. Okay, and of course it could be, let's say, between 180 to 270 as well. It is directly proportional with the angles between the two as well, but we said we're not going to focus on this, and that is what we have. We said, remember this, this torque causes rotation. We said torque is measured in Newton meter. That is the SI unit for a torque. Torque is a vector quantity. We said if the rotation is clockwise, it is negative. If it is counterclockwise, it is going to be positive. And if we have more than one torque, we could just add them. We could algebraically add them together. For those that are in the same direction, we add them. And of course, for those that are opposite, we'll just subtract them once we find the total. That is clearly what we've studied last time. Today now, and of course, we solved some questions too. Today we have another question, which is one of the questions that we have. It is very simple, but yet, of course, there could be some changes, or they can add or make some changes regarding this one. So the question might change here. So I will need you to pay attention here and see how we can solve this question. So first, let me bring the whiteboard back to this point here. All right, so what do we have for this question right here? It says, a simple pendulum consists of 3 kilogram point mass and hanging at the end of a 2 meter long light string that is connected to a pivot. Now in physics, of course, whenever it says something is light, that means ignore the mass of the object. So whether if it is a string, whether if it is a beam, or it could be anything else, which you will need this one later as well here. Okay, so we have a pendulum. This is a pendulum, by the way. It is a mass. The name of this mass, the name of this mass is called Bob. Okay, it is connected to a string. This pendulum, just like a swing, for example, once you pull it back, then let it go, it is going to swing back and forth, back and forth. That is clearly a pendulum. So here, the mass of this pendulum that is given, it is 3 kilogram. So this is the mass, we could say. Let's choose this one. Okay, so this mass, it is 3 kilogram. And then the length of this string here, it is 2 meter. Okay, so here's a question. It says, calculate the magnitude of the torque due to gravitational force around this pivot point when the string makes 5-degree angle with the vertical. Now, I need you to focus on this part right here. It says this pendulum, it is going to make a 5 degree with the vertical here. So now at this point, we could say this is where the mass is. This is the angle. It makes 5 angle with the vertical. And by the way, whenever it comes to angles, you can write this as a note as well. Whenever it comes to angles with the pendulum, the angle must always be with the vertical. If not, you'll have to find the angle with the vertical. This angle is 5 degrees. And then, but at this point here, I need you to focus at this one here. Now this mass, right, would analyze to, because the force of gravity is always directed downward here. This mass, of course, it produces an Fg, which is equal to m times g. This thing here, okay, this Fg now, it is going to analyze to 2 components. One of them, you can call it Fg sine theta. And by the way, before we let it go, this is 5 degree, and this angle is going to be 5 as well. These are, remember, you can call them alternating angles because they have the same case or the same position here. So these two angles will always be equal to one another. This is why it's so important for the angle to be with the vertical as well. So because the angle is with this side here, so we know that this side is going to be FG cosine theta, and then the other side is going to be FG sine theta here. Now, which one is the perpendicular component, or which one causes the rotation here? It is this component, FG sine theta. So FG sine theta is going to be the same as this. This is the length. You can say it's the distance, and this is where the force is. Okay, now these two, of course, cause a rotation where the pendulum is going to rotate or swing back and forth in here. So if we want to find the torque here, we'll just say F times d sine theta. Once again, the force that we don't have the force, but we have the mass, so we can say mg. So now the mass is 3 kilogram times 9.81. That'll be the force times the distance, which is going to be the length of the string here, times 2, and then sine of the angle theta, which is at this point here. Remember, I said these two angles will always equal to one another. You can see that this angle is also with the distance as well. You can see that. Remember, this is not the angle that you use, this one, so we'll just say sine 5. Okay, and now you do the math, you'll find the answer, which is going to be this much Newton meter. You might say, what about the direction here? Well, if the question does not talk about which way it is rotating, we just assume that we didn't hear it. So in that case, if the question does not tell you which direction it is rotating or which way it is, then you don't have to tell the direction. You just find the magnitude of the torque, which means only the result or the value. But there's something else regarding this question which I would like you to know. Okay, perhaps maybe after this. That is all part A, you can say. Part B says repeat this calculation for an angle 15, so you're going to do exactly the same thing, but the only thing, you're going to change the angle here. Instead of 5, you're going to write 15 here, so the rest of the thing is always going to be the same here. Let's say that is going to be part B. The force is 3 times 9.81, right, times the 2, which is the length, sine 15 degrees. You'll find the answer, which is going to be Newton meter. That is the torque when the angle is 15 degrees with the vertical here. Now, there is one idea in this thing here. What if there might be, of course, a question in Wizari that might ask you this question this way. We know that, first of all, let's just consider the pendulum at this point here. We know that this is Fg. If the mass of the pendulum, whatever it is, that mass becomes Fg. We know that, m times g, right? And then, so gravity pulls the mass down, but what stops the mass from moving downward? Isn't that the force or the tangent force which is inside the string here? Yes. So when these two are equal in magnitude and opposite in direction, then the mass will be balanced. It is not going to move downward or upward in here. So, but this must give you an idea here. So if the pendulum is not swinging back and forth, these two are equal to one another, and at this point, the angle is 0, so there is no net torque here. But now, the same case, I want you to focus at this point here. So this is the pendulum, the second case, let's say. Let's just bring a line. So here's what we have, let's say. This is the pendulum that we have. Okay, so here's the pendulum again. We said that this mass, it will divide into two components here. One of them, these two angles are always the same. Okay, so this side is F tangent now. You could see that. And the other side is going to be FG cosine theta. This side, we said it is FG sine theta here. Okay, so this is the side where it causes the rotation. But what if the question says, what is the tangent in the string here? Okay, never been an Uzari, but what if this question came? It's exactly the same, no different question and no different nothing. Remember, these two are always equal in magnitude and opposite in direction. So if the question ever asked for the tangent at this point here, remember, if it was at this point, we could have just said FG. But now, because we have an angle here, so tangent here, tangent force, it is equal to FG cosine theta. Remember this, because these are on the same line here, one upward, the other one is downward, equal in magnitude, opposite in direction. So clearly the force would ask for the magnitude here. So Fg would be mg. The mass is 3 kilogram, or yes, times g, 9.81, right, times cosine 5 degrees in here. So of course you can find the magnitude of the tension which is inside the string in order to hold the mass. So pay attention to this one as well. That is also an idea which has not been in a WSAT yet. All right. What if, by the way, what if the angle that is given is with a horizontal? Let's say this angle that is given, let's just say, remember we said whenever it comes to pendulums, the angle must always be with the vertical. If not, change that. So what if this angle is given? Right, let's get this one back. See, this is, okay. Now, what if the angle that is given is with a horizontal? Let's say when we say with a horizontal, that means this angle. Let's just say that this angle is 80, let's just say. Remember, this is not the angle that you're supposed to be using, so we'll say 90 minus 80, that is going to be 10, so this angle is 10. Then now these two angles are the same, and then for the torque, you could just use mg, or torque, it is equal to fg sine theta, then you can use the angle here, or you can find the torque. All right, now we have another question which is also easy. It says, if the torque required to loosen the nut here, if the torque required to loosen the nut on a wheel of a car has a magnitude of this, so this is, or what is given as a torque, it is 40 Newton meter, what minimum force must be exerted by a mechanic at the end of a 30 centimeter, so this will be the distance, wrench to loosen the nut? Clearly that is easy enough, so we'll say torque it is equal to force times distance. Since no angle is given, this is 40, says what is the force, minimum force needed, times 0.3, so you can easily find the force at this point here. So force it is equal to 40 divided by 0.3, whatever the math is. You do the math, so you'll get 133 Newton. That is how much force is needed to loosen the nut. Okay, now we have another question which is also interesting. Says, a bucket filled with water has a mass of 54 kilograms and it is hanging from a rope that is wound around 0.5 meter radius stationary cylinder. If the cylinder does not rotate and the bucket hangs straight down, what is the magnitude of the torque that the bucket produces around the center of the cylinder here? All right, well, I think we could still do that on the other side here. So let's just do that here. Okay, so maybe we'll get this whiteboard here. Watch this one here. So now you can, of course, write a note at this point here. Whenever it says we have a cylinder, we have a pulley, we have anything that looks like that, and the mass is given, you can always use the mass multiplied by g to get the force in here. So here's, let's say, the cylinder that we have. Here's the force is acting. Sometimes you can call this one the tangential force, makes no difference, because we've learned that in chapter 1, there is a straight line that touches a circle, you can call it tangent, right? So here's the bucket. It has a certain mass. So this mass, of course, produces Fg. Or whenever you have a mass, you can immediately say multiply by g to get Fg here. So there's where the force is acting here. And then there's the radius of the cylinder, you could say. Can I say this radius will be the distance? So this force and radius produce a torque, even though the cylinder is not rotating here. So the torque's, anyway, we don't need that one, or we don't need this extra information for now. Just remember, this to produce a torque. What is this torque in here? We can say force times distance. No angle is given, so that is perpendicular, which means the angle is 90, you could say. If not, you don't have to worry about this. Instead of the force, we're going to write mg. Here is mg times the distance here, or you can say the radius here. Okay, so what is the mass? 54 kilograms times 9.81, and then multiply by the radius, which is 0.05 meter, or 50 meter. You do the math, of course, you'll find the answer, which is going to be 26.4. 26.4 Newton meter. Once again, if the direction is not given or mentioned, we don't have to worry about that. You'll just find the magnitude of the torque, and that'll be it. All right. Now remember this note, it says in cylinders, pulleys, and disc, the torque, all right, it is equal to force times distance. Of course, the mass or this force would be mg, and the distance would be the radius. We have a question similar to that. All right, I'll do the steps so you can find the answer. It says what? A bucket filled with water has a mass of this much, so this is the mass, is attached to a rope that is wound around a cylinder with a radius of, so this is the radius, at the top of the well. What torque does the bucket produce on the cylinder? So we can say the torque is equal to force times the distance here, but the force would be mg, and the distance would be the radius. So the mass is 22.5 times 9.81. This would be the force times the radius, which in this case represents the distance. So you do the math, you'll find the answer, which is going to be 11 Newton meter. Okay. Now, section 2.0 or section review 2.1, you could say, we have a question says, in which one of the following situations should the object or objects be treated as a point mass, and in which situation or which one of them should the object or objects be treated as an extended object? Now, of course, we haven't explained this one, so I need you to turn to page number 81, right? Because there's a concept needs to be explained so that we can answer this question. What is this concept? It says rotational and translational motion can be separated. And how do we separate rotational and translational motion here? Now, of course, up to this point, because let's say grade 11, we had objects moving in a straight line. So these things or anything that moves in a straight line, we call them translational motion here. But because this year we're dealing with circular motion or rotating objects, so objects are rotating. So how do we differentiate between translational and rotational object? Now, I want you to focus on one detail here, which makes it very easy here. Now, for those objects that are not rotating, we call them a point mass, or just we call them a point mass because if it is just, we treat them as if they were a point mass, regardless to the shape or, let's say, size or how they move, as long as they move in a straight line. For example, now if a car is moving on a straight line, let's say we consider that car as a point mass. We know that the shape of one car is different to another. There are different parts of the car, maybe there is even the wheels, but for the sake of studying the car's motion that is moving in a straight line, we just consider that as a point mass. The car as a whole, don't forget. And then what if we have, let's say, a bowling ball, and if we allow the bowling ball to roll down on the surface here, we know that it is, let's say, rolling, so it is spinning while it is moving. So for those objects that are rotating, that are spinning, we call them extended object. Even if they are not moving, as long as they're spinning, we still call them extended objects here. So what are extended and point mass and extended objects? Once again, for those objects that do not spin, right, we call them point mass. For those objects that are spinning or spinning and moving together, so we call them extended object. Let me give you an example. Think of this, for example, pen. If I just drop them, you can see that it drops without rotation. So I'll consider the motion of this pen as a point mass. But for example, what happens if I allow this pen to roll down on a table? Let's say you can see that it will be rolling while it is moving, right? So in this case, the same pen, it can be considered as an extended object because it is rolling. So remember, there are some keywords. Whenever it says an object is dropped, an object is moving in a straight line, let's say, without a rotation, or if it says without a rolling, these are keywords that these objects are considered as a point mass. But as long as it says an object is rolling, so that is a good indication to know that the object is an extended object. So watch this one here. It says, recognizing the difference between point and extended mass, right, or extended object, a point mass can have translational motion only. Like, for example, if you drop a ball from the roof of a house, the train movement, these are objects where they go in a straight line without rotation, so we call them point mass. On the other hand here, it says, while extended objects basically can exhibit or have both rotational and translational motion. So, for example, like Earth rotating, let's say, on its axis, or you could, if you remember fidget spinners, for example, you could do that. They are just spinning like a Ferris wheel, let's say. These are just spinning. So for those objects that are spinning, we call them extended object. What if they are spinning and moving? Like if you roll a bowling ball, or the pin, or let's say the motion of a pin or a bowling ball, these are both called extended objects here. So whether the object is just spinning or spinning and moving at the same time together, these are called extended object here. So I need you to remember this study tip, and the most important thing is the line at the bottom here. It says translational motion of an object can be described as by assuming it as a point mass, while for an extended object, like a bowling ball or a pin, can demonstrate both the rotational and translational motion. But here's one thing you need to know. Objects undergoing rotational motion cannot be treated as a point mass. Okay? So those objects that are, basically undergoing rotational motion, they cannot be treated as a point mass. They're called what? They're called extended object. But watch this point here, which is also very important. Even if we have an extended object, if we want to study their translational motion, for the sake of studying their translational motion, we can consider their motion as, or we can say we can ignore their rotational speed so that we could study their translational speed. So it is possible for an extended object, right, to ignore its rotation so that we can study or analyze the motion or the translational motion of the center of mass of that object in here. So now, to summarize all what I said, remember this. If an object's center mass, let's say if it is spinning, we call it an extended object. If it is not spinning, we call that a point mass. But I need you to know one thing actually. There is one thing you have to be careful, and that is the motion of the Earth. Because Earth has two types of motion, right? One of them, it is rotating on its axis. That is clearly because it is rotating, we call it an extended object. But what about when the Earth is traveling around the sun? Remember this. Now, even when Earth is traveling around the sun, it is both rotating and, of course, moving at the same time. But for the sake of studying it is translational motion, whenever you see Earth or saying Earth is traveling around the sun. So if something is traveling, clearly we consider, or we're studying their translational speed. So in that case only, we're basically ignoring their rotational motion. So if you remember, we said Earth traveling around the sun is considered as a circular motion, which was categorized as a translational motion as well. So in that case, of course, we consider the motion of the Earth moving, or let's say traveling around the sun, as a point mass so that we could study the motion of the Earth around the sun. Don't forget that. That is not an exception, but you can think of an exception, because in that case, of course, we're totally ignoring their rotation. And how do we know we're ignoring? Because the question would be telling you Earth traveling around. So we use the word traveling when there is a point mass clearly. Okay, so now let's go back to the page that we just left here. I think, what was it, 87? 70 something, what was it? Okay, so let's go back to the question and see if we can answer these questions here. The first one says, but remember the note here, I've tried to copy it here as well. If the center of the object spins, that is a rotate, it is extended. If not, it is a point mass. So watch these things here. It says a ball dropped from the roof of a house. Once again, if you drop a ball, just you drop it, there's no rotation, so it is a point mass. But what if you allow it to roll down, let's say? Or you kick the football, which is clearly moving or rolling on the surface, that'll be extended. But here, because it is just dropped, no rotation, so it is a point mass. What about a ball rolling? See the keywords here? I need you to underline these keywords for yourself. Whenever it says something is dropped, so clearly there is no rotation, unless if it is dropped with a rotation, that'll be a different case here. And says a ball is rolling, so rolling, that is clearly, so dropped here, no rotation. Here, rolling, it means there is rotation. So you can underline this and write a note for yourself. A ball rolling towards the goal, that is extended. What about a pinwheel in the wind here? So here's a pinwheel, and you know that if there is a wind, for example, coming or blowing, it can rotate this pin, you can say pinwheel here, which is, of course, an extended object because it is rotating here. Need you to be careful with this tree here. Let me start with E first. It says Earth rotating about its axis. We said if it is rotating, of course, that is extended, right? What about D? It says Earth traveling around the sun. We said, remember this, because as traveling around the sun, we ignore the rotation part, so we'll consider the motion of Earth traveling around the sun as a point mass. Don't forget this. All right, now we have another question. Says, what is the rotational analog of a force, and on what quantities does it depend on? That is, previously we've mentioned that the rotational analog of a force, in rotational motion, it is the torque. What does torque depends on? It depends on force, distance, and of course you can say the angle which the force is acting as well. So we can say it depends on the force in here, depends on the lever arm or the distance. The scientific name for this would be the lever arm and the angle at which the force is acting. So these are the three things that the torque is depending on. Okay, now we have another question here. This question is very interesting, actually. It is one of the easy questions that we have, but for some reason, some students sometimes get confused when it comes to this. So let's get rid of the confusion and make sure you fully understand this one. Okay, so it says calculate the torque of each force acting on the bar. So first of all, I need you to know how many forces do we have. There are three forces. This is one of them. Let's get this one back. Okay, so this is one of them. You can call it F1. And this is another one. You can call it F2. This is the third one. You can call this one F3 if you like. It says, assume that the axis is perpendicular to the page and passes through point O. Where's point O? Here's point O. So this is the axis of rotation. All right, you don't need this. You just remember this is the axis of rotation. And that's it. It says in which or what direction will the object rotate? So after you do this, what direction will the object rotate? And I'll also give you, inshallah, some other ideas that it might change regarding this question. So first of all, let's try to find this one here. Okay, so the first thing that we're going to do is we have to calculate the magnitude of each torque and see which direction they're acting so that we could do this properly here. Let's keep the diagram here. Okay, nope. Let's go back to this one. Or maybe we should move this one a little. All right. So that is what we have. I need you to watch closely and see how you can do this one easily without making any mistakes, inshallah. So the first thing that we have is this. Right, I think I will not redraw the diagram since you already have it here. So how about let's start with the first torque in here. Now, you tell me, what is the torque of the first one? Let's change the color here. Okay, so what is the, let's say the torque of the first force? Let me just call it torque of 30 Newton. If you remember, we said if any force is acting or passing through the axis of rotation, what would be the torque in that case? Do you remember? We said if this is the axis of rotation, by the way, yes? That is the axis. You can see that this force is passing through the axis of rotation. Now, of course, don't fall for this one, the angle that is given or whatever, no. Because this force is acting or passing through the axis of rotation, there's no torque for this one. So you could say right away, the torque for 30 is going to be 0 Newton meter, and that's it. So that is the first one here. You could say, what about the second one? Okay, so this is the first. Okay, now what about the second one here? So for the second one, again, we can say torque of, what is the other one there? Okay, so clearly the second one, it is going to be torque of 25, yes? I don't see the numbers there, but here. So that is force times distance because we have angles here. So we'll just say sine theta. You agree, right? What is the force that we have? All right, that is 25 times. What is the distance? Watch this. Right, the distance from where the force is acting all the way to the axis of rotation, that is 2 meters right here. So we'll just say times 2. Now, this thing I need you to be careful here. Remember, the angle that is given is 31, but is this angle between the force and the distance? No. that is between the force and the normal, and we're not going to use this one. We said we'll always have to use the angle that is between the force and the distance, which is this angle right here. But how do we know this one? We know that this is a right angle. So can I say 90 minus, as you can see here, 90 minus 31? If you do this one, of course, you'll get 59 degrees, which means that this angle is 59 degrees in here. So just sine 59 degrees. So you could do the math, but before that, what about the direction here? So here's the axis of rotation. Remember to do this always, right? This is where the force is acting, so you could once again place one end of the pen right on the axis of rotation, and then you could use your fingertip or another pen just to apply force, even the same direction. You could see that it is going to rotate counterclockwise, which means it is positive here. All right, so whatever the answer is, you will just write it down. Let's see, what is the answer? The answer for this one is going to be 43 Newton meter. Now that is for the second one. What about the torque for the third one here? And here's the third one. Watch this. The force that I have is 10, right? What about the distance? The distance from this point all the way to the axis of rotation, that is 2 meters. So the other side is 2 meters. That is a total of 4 meters here. So we'll say the torque of the 10 Newton, force times distance, sine theta here. Once again, the force is 10, the distance is 4 times sine theta. But look, is this angle between the force and the distance? You might say there is no more distance. Well, you could extend it just a little. Here's the distance, right? So is this angle between the force and the distance? Yes, okay, because this would be the normal, let's say, if we consider the other side here. Okay, so it's not with this angle. So clearly it is attached to the distance. So we'll just say sine 23. And then once again, regarding the direction, is it clockwise or counterclockwise? If you use, for example, a pen that is long enough until it gets to this point, so once you do this, of course, you can see that it is clockwise. But here's one thing I need you to be careful. Some students might think that because this one is acting at this point, so the force for this one must be, or the torque for this force must be 0 too. No. Why is not? Because, watch this one. Is this force acting, here's the axis of rotation. Is this force acting on the axis of rotation? No, because here's the axis of rotation. So this force is normally acting on, you could say, on this part of the beam here. So it causes rotation, which is just fine at this point. So all you have to do, just do the math and that's it. So this one, because it is going to be negative or clockwise, so you add a negative here. The answer to this one is going to be negative 16 Newton meter. Now, the next thing that is left is you have to find the total, the net. So how do you find the total or the net? We'll say the net torque, it is equal to torque 1 plus torque 2 plus torque 3, we could say. Torque 1, it was 0. Torque 2, it was positive 43. And then plus torque 3 it is negative 16. Once you do the math, of course, you will get positive 27 Newton meter, which means that the beam is going to rotate counterclockwise, or it is just going to rotate that way. And that is how easy this question can be. Now, what could be different, or what could change about this question here? Well, what if, for example, this, watch this one here. The things that could change about this one here, maybe they can, instead of making this side, for example, the axis of rotation, they can make this side the axis of rotation, which is totally fine here. In that case here, if that is what they do, then remember this torque, or the torque that is provided by 10, right? For this case here, this torque is going to be 0. And then this one here, watch this, you're going to do exactly the same regarding this one here. And then for this one now, it is going to cause some rotation, because here's would be the axis at this point here. So let me tell you how you can calculate each one of those here, starting from this force, that is, what was the magnitude of this? 30. And this force was 25. And you could just simply do this one here. So let's just say I'll do, like I'll show you how the steps, and you could do the math for yourself. To find the torque of 30, you could have just said, for example, force times the distance here, sine theta. Okay, so for this one, the force is 30, times the distance from this to the axis of rotation, that is going to be 4 meters, times sine 45, by the way, because this 45 is between the distance and the force, so that'll be 45. Now torque 30, torque 25, but let me not forget the direction, by the way. If this is the axis of rotation here, so the force would be acting in this case. So in this case, of course, it is going to rotate the beam clockwise. If it is it is going to rotate the beam counterclockwise. If it is counterclockwise, it is going to be positive. Once again, you could do this. This is where you apply the force, right? Like I said, sometimes I avoid using this because it would interact with this one here. So, but once you do this one, if you apply force there, this is how the pen is going to move, right? So is it this way of moving? Is it clockwise or counterclockwise? You can, of course, give it a full rotation. So this way of movement, it is, you can see that it is counterclockwise. Counterclockwise, which means positive, whatever the value for this one, that is going to be positive this much Newton meter. That is for this one here. What about for the 25 Newton? So we could say for the torque of the 25, it is force times distance sine theta. The force is 25. The distance, watch this, from this to this, that is 2 meter, times sine, the same method that we did. So we're not going to use this angle. We'll have to use this one, which is 59. Okay? And then whatever the answer is, it's going to be this much Newton meter. What about the direction here? So if that is the case here, so if you apply a force there, this is how it is going to rotate. And this way of rotation, it is going to be clockwise, which means this is going to be negative. What about for, let's say, torque of this one here, torque of 10? We said earlier that torque of 10 is going to be 0. Now you could just add this 3 together to find the total, and that would be it. There's one more possibility of changing this one here. What if they made the center of the beam as the axis of rotation? That is also possible. If they make the center of the beam as the axis of rotation, in this case, this force of 25 Newton would produce no torque. And this is 31. Like at this point, doesn't matter. So here's what we have, 10 at an angle of 23. And then here we have 30 at an angle 45. So once again, if this is the axis, these two would produce torque. Don't forget, this is going to be clockwise and this is going to be counterclockwise since this is the axis of rotation. You just normally do the math and that's it. So for torque 30, again, force times distance sine theta. The force is going to be 30 times the distance is going to be to the center, that is going to be 2, times sine 45. Whatever the number is going to be positive this much because it is clockwise, counterclockwise, Newton meter. The torque for 25, it is going to be 0 because it is right on the axis of rotation. All right, and then for the torque of, let's say, the third one, the torque of 10 Newton, it is going to be 10 force, you could say. 10 times the distance, which is 2, from the axis, sine 23. And this is going to be negative. So whatever the answer is, to find the total, you add this 3 together, see whether the torque is positive or the net is positive or negative. If it is positive, clearly the final rotation is going to be counterclockwise. If it is negative, it is going to be clockwise. And I hope you understood this. Now we have some other questions here. It says, how would the force needed to open the door change if you change the distance? Sorry, this one is... All right, it says, how would the force needed to open the door change if you put the handle in the middle of the door? So as you can see here, this is, let's say, these are the hinges where the door is rotating. This is the doorknob. So that is basically where you apply a force right at this point here. Here's a force at a perpendicular distance here. So the question says, how would this force change if you put the handle right in the middle of the door? So clearly making the distance half. Now, how much torque is needed to open the door is fixed, you could say, or that is a constant. So we can say torque is equal to force times the distance, right? Now, I need you to watch this very closely. If the distance is going to become, let's say, half, it means 1/2. What is the easiest way to solve this one here? Always remember this. By whatever the factor the distance is changing, the force must change by the reciprocal of that. So if this is by 1 over 2, then the force must change by 2 over 1. Why? Because these two must always cancel out so that we can always get the same amount of torque, because that is how much is needed to open the door. What if it says, let's say the distance is changed to 2/3 of, let's say, the door here. In this case, of course, you take the reciprocal of this one, so the force must change by 3 over 2 so that this will always cancel out. We get the same amount of torque. So if you do this, this reciprocal method, of course, would help you a lot whenever we have two things that are inversely proportional. Because remember this, when it comes to torque, we know that it is directly proportional to the force. Torque is directly proportional to the distance. But the distance and the force are inversely proportional, don't forget, for a constant force. Okay? That is what we have. So by whatever the factor, the distance, or even the force is changing, the other one must change by the reciprocal of that factor. Okay. By the way, what if it is not by a factor, let's say? What if the distance becomes doubled, let's say? So by what factor will the force should change? We said use the same thing, right? So if the distance doubles, just watch this one. If the distance is double, that is not a fraction, right? But you can make it a fraction. So in this case, of course, the force must change by a factor of 1 over 2 so that we can always get the same amount of torque. Now here's another question which came in last year's preparatory exam. It says what? It says, how does the length of a pedal arm on a penny farthing bicycle affect the amount of torque applied to the front wheel here? Okay, so once again, because the torque is directly, the question says, how does the length of the pedal arm, the distance on a penny farthing bicycle, affect the amount of torque? It affects the torque in here. We know that. What is the relation between the two? Are they directly proportional? Yeah, so we can say the bigger the length of the pedal arm, that means the bigger the torque. Or you could say increasing the distance increases the torque. That is also fine because these are directly proportional. By the way, penny farthing bicycle, it is these kind of bicycle who have a giant front wheel and the pedal arm is directly connected to the front wheel, but the you could say the second wheel is very small. Okay, here we have another question which is also interesting, this question. And there are other ways, by the way, where this question can change as well. What does it say? It says the arm of a crane at a construction site is 15 meters long and it makes an angle of 20 degrees with a horizontal. We need you to be aware of these information here and you can underline them for yourself. So the arm of a crane at a construction site is this much. That is the distance, right? Okay, it makes that at this much degree with the horizontal. Make sure that you know what is this. Assume that the maximum load the crane can handle is limited by the amount of torque that the load produces around the base of the arm. Part A says, what is the magnitude of the maximum torque? Okay, what is maximum torque the crane can withstand if the load, or if the maximum load the crane can handle is this much Newton? It says Newton, that is a load here. Even if you didn't know what a load is, you should recognize this by the Newton here, which is clearly that is the force here at this point. Okay, that is part A. Part B says, what is the maximum load when the crane makes an angle 40 with a horizontal? So let's do this one properly here. Remember, let's say this is the length of a crane arm here. Okay, so this crane arm, it makes 20 degrees with a horizontal. So let's say that is what we have. Okay, let's draw a few more lines. So this is the horizontal. It makes 20 degrees with the horizontal. Okay, so this is 20 degrees. And it says this crane arm is 15 meters long. Okay, so there is a load in here. This load is, you could say here's a load, which is 450 Newton downward here. So the question says, what is the maximum torque that the load can produce about this space arm in here? So simply, we know that torque up to this part, so there's nothing, like difficult with this. Force times distance sine theta, right? And that is what we have. So what is the force that we have? The force is 450 times the distance is 15, right? times sine theta here. Now, at this point, you have to pay some attention to this one here. So what makes it a little bit different here is this angle right here. Do you remember we said the angle that is given, let's say, must always be between the force and the distance, must be attached to the distance? Yes, but where's the force? Here's the force, and here's the distance, right? Is this angle between the force and the distance? No, this is the horizontal, you could say, right? Or x-axis, if you want to call it whatever, right? So this angle, as you can see here, it is not between the force and the distance. As a matter of fact, this is the angle where it's between the force and the distance here. This one right here, yes? This is the angle that we're supposed to know here. But what is this angle exactly? Well, we don't know. But is there any ways where you can find that? Yes. We know that this is, or this one, clearly making a triangle. In a triangle, the total angle in a triangle, it is 180 degrees. Now, clearly, we have, this is obviously 90, and this is 20. So can we find this angle here? Yes. So there is another easier way, actually. So you could say the total is, or you could say theta 1 plus 2 plus 3 must equal to 180. But there's something even easier. 180, of course, it is equal to 90 plus 90. Yes or no? You add this two, you get a total of 180. I already have one of the 90s here. Can I say these two angles together must make the other 90? Yes. One of the angle is 20. So what is the other angle that I must have so that I can get a 90? That is 70 here. And that is that easy here. All right. So now this angle here, it must be 70. Once again, now you can add 20 plus 70, that is 90, 90 and 90, that is 180. That is how you can find this one here. So the idea regarding this question, it is the only thing regarding this question is this angle. Once again, the angle that is given, you're not going to use that angle. Why? Because that is not the angle between the distance and the force. Here's the angle between the distance and the force, which you have to find it. All right, I hope you understood this. Okay, if not, we're going to do this one in the second part again one more time. So now we'll just say sine what? Sine 70. So once you do this, of course, you will get 6343, if I'm not mistaken, Newton meter. That is basically the maximum torque that the crane can, let's say, have or handle or whatever, withstand, let's say. That is how much torque it can produce. All right, what is the second part? It says, the second part says, or part B, you could say, it says how much torque or how much load, let's say, this crane can withstand if the angle is 40 with the horizontal. Now this angle, it becomes larger, 40 with the horizontal. So once again, how much load can the crane, let's say, hold or withstand at this point here? Remember, the distance is still 15. And then at this point, we have the maximum torque from part A as well. So we'll say maximum torque, it is equal to force times distance. This force is going to be maximum, of course, times sine theta. Once again, 6343. It is equal to the force that we have, it is unknown this time. And then the distance is 15. Once again, what is the angle this time? Remember this. So this is already 90. Right, 90 plus 90. I already have one of the 90s, so these two angles together must make 90. If this is 40, what is this angle? Can I say it is 50? Yes, 50 and 40, of course. It makes 90, so this time I'll just say sine 50. And once you do this, of course, you can find the maximum force, which is equal to 6343 divided by 15 sine 50. So once you do the math, you will find the answer. Let's see what are the answers instead of using a calculator. All right, so 6343, that is for part A. For part B, the maximum force we can have, or the load can, let's erase this. Perhaps there is an issue. All right, so it is going to be 552 newtons. 552 newtons. This is how much load the crane can, for example, have when this angle is 40 with the horizontal. Now, what would be the ideas, for example, or what are the things that can change? Maybe we could do the reverse of this. What do I mean by the reverse of this? The question can give you the same thing, but this time they can ask for the angle that this crane makes with the horizontal. Let's say this is the crane arm, and here's the load, let's just say. And here's the, let's say, the angle. The question might say the distance is still 15. Let's say the load that this crane can have, let's just say it is 450 Newton. And then the question will also give you the torque as well. Let's say the torque, it is 6343. The question might say, what is the angle? Let's just write the question here. What is the angle the crane makes, or let's say the crane arm, makes with the horizontal? All right, watch this. This one is a bit tricky. Let me tell you why. Because when you find the torque here, torque it is equal to force times distance sine theta. So normally that is 6343. It is equal to the force, which is 450, times the distance is 15 sine theta. This theta here, it is unknown. So clearly you would say sine theta it is equal to 6343 divided by 450 times 15 here. We want theta here, so theta it is equal to sine inverse of this much, 6343 divided by 450 times 15. So this is how you can find theta here. But this theta you find, it is going to be 70 degrees. Okay? And of course you will see 70 degrees in the choices as well. But remember, that is not the answer. What you have found is normally this angle that is from the equation, this angle, that is always the angle that is between the force and the distance, which is this angle that you found here. So you found this angle, which is 70 degrees. But what is the question asking? It says, what is the angle that the crane arm makes with the horizontal? Okay, so this is the exact reverse of what we have. So the question wants this angle. So how do you find this angle? Now, once again, this is 90, this is 70. So how do you find this angle? The same method that we said. The total angle in a triangle is 180, which is 90 plus 90. The reason why we're doing this, because we already have this. These two angled together must make 90. I have one of them, which is 70. What is the other one to make 90? It should be 20. So the angle that the crane arm makes with the horizontal, it is 20 degrees. Need you to be aware of this one too, because these ideas have not been in Wazari. Now there's one more idea that they could ask, but this one is way easier than what we just said. And that is if they gave you, for example, the angle, instead of giving you with a horizontal, they might give you with a vertical, let's say. Here's the crane arm again, that is the distance, 15. Instead of saying it makes 20 with a horizontal, what if they say it makes 20 with a vertical here? So maybe not even, let's say 20, let's use I don't know, maybe a decent angle here. Let's say it makes 60 with a vertical. So once again, in order to, here's the load, 450. In order to find the torque, you still have to find this angle. But if that is the case, these two are way easier. Remember, these are corresponding angle. So whatever this angle is going to be exactly the same as this. So it is way easier. In this case, torque it is equal to force times distance sine theta. The force is 450. The distance is 15. Sine 60. You could just easily do the math, and that's it. Even if they were asking the angle with the vertical, once you find this one, it is exactly equal to this two, and that is. But when do we use this? Only if they say the crane arm makes this angle with the vertical. That'll be with the y-axis. That was also an interesting idea, but I hope it won't be in Wazari. If it ever come in Wazari, hopefully it's the same as what is written here. Okay, let's see if we can erase this. That's a bit odd. Okay, so we're just going to move on. Scroll down. Now, at this point here, we have another question. Says a wooden bucket filled with water has a mass of this much, because we have two parts here. This one is sort of related to the rotational equilibrium. I would like to skip this one for now, leave it for later. Once we study rotational equilibrium, then I'll come back to this one, because then it makes it easier to understand this one. Once we study rotational equilibrium, then we'll get back to this one. Why? Because it says the bucket moves at a constant speed, because there will be torque. The torque, both the clockwise and counterclockwise, are going to be the same. And then you could just easily do the math. But that'll be for later. You can see that this question is exactly the same as the one that it came above, or we just solved above. So give it a try, see if you can solve this one on your own here. Okay, let's move on to another question. It says if the torque required to loosen a nut is very similar to the other one that was similar to this one here, but this one, there's one slight difference here. Here we have an angle. But you can write a note for yourself as well after me completing or completely reading this. It says if the torque required to loosen a nut that holds a wheel on a car has a magnitude. So this is the torque, has this magnitude, 58 Newton meter. If you didn't know this one, you can always rely on the unit. So Newton meter, that is a torque. What force must be exerted? So the force is unknown here, correct? Be exerted at the end of a 0.35 meter lug wrench. So that is the distance of the, you can say of the lug wrench to loosen the nut when the angle is 56. So write this. If the angle is neither mentioned with the x-axis or y-axis, or let's say if it's not mentioned, the angle is with a horizontal or vertical, that is, we'll just use that equation. So you don't have to worry about, do I have to subtract from 90? When do I subtract, when I don't? If the question does not tell you which angle or which side this angle is with, that is the angle they want you to use directly. So that means you don't have to worry about this. So in this case, so the torque, it is equal to force times distance times sine theta. That's all what you need to do. The torque that we have, it is 58 Newton meter. It is equal to, the force is unknown, the distance is 0.3, and then 0.35, my bad, and then times sine theta, which is 56 degrees. Now all you have to do, make force the subject, 58 divided by 0.35 sine 56. You do the math, you'll find the answer, which in this case, the force is going to be equal to 200 Newton, and that is how you can easily do this one here. So once again, remember the keyword. If the question does not tell you which side is the angle is with, you can right away use the angle. Okay, now we have one more question here. I'm afraid we might not have enough time, but we're going to give it a try. This question is also one of the important questions that we have, and of course there are other ideas which it can be asked regarding this question as well. What does it say? It says a 23 centimeter screwdriver is used to pry open a can of paint. If the axis of rotation is 20 or 2 centimeters from the end of the screwdriver blade and a force of 84.3 Newton is exerted at the end of the screwdriver's handle, what force is applied by the screwdriver on the lid? Now, I want you to watch this. Let's say here's a screwdriver. Okay, let's just say this is the screwdriver. The question itself tells you that the axis of rotation, it is 2 centimeters. The length of the screwdriver is 23 centimeters. The question tells you that the length or the axis of rotation is 2 centimeters from the end of the screwdriver. All right, if this is the length of the screwdriver. Now, if this side is 2 centimeters, what is the remaining length for the other side? Isn't that 21 centimeters? Because that is a total of 23 centimeters. Once again, this side here, we have 84.3 Newton. Let me double check the number. 84.3 Newton. It is exerted at the end of the screwdriver here. What force is applied by the can of paint in here? So clearly that is, this is used to pry open a can of paint and whatever it is. Now remember this, sometimes we use the screwdrivers basically the tip of the screwdriver goes under, and then you could just, for example, pry open this here. So, but at this point, you don't have to draw the whole thing here. What force is exerted by the can of paint, let's say, at the screwdriver here? So clearly, we could say the torque of this side must be equal to the torque to the other side here. Because we have torque on both sides, these two forces must be equal in magnitude and opposite in direction in order to do that. So we can say the torque at one side must equal to the torque at the other side. You can call this one counterclockwise, the other one clockwise, but at this point it really doesn't matter which one is clockwise or counter. Just the torque of one side must equal to the torque to the other side. So we know that torque is equal to force times distance, no angle is given here, must equal to force times distance, and that's it. The force for this side, it is unknown, so we'll just rewrite it, times 2 centimeter. You could say, by the way, at this point, because we have centimeter both sides here, even if you don't convert, that is totally fine. But I'll convert them anyway, so that you don't forget to convert once it is needed. All right, that is this, multiplied by 84.3 times 0.21, if you convert to meter. Then now, all you have to do, just find the force, which is equal to 885 Newton. This is how much force is applied by the can of paint at this point here. Now, how about if we change the question at this point here? That is how easily you could do this one. But consider, just assume that, or imagine, we have the same situation, but this time, the length of the screwdriver is required. Let's just say, here's the axis of rotation, which is, again, this is not to scale, but let's just say this is 2 centimeter away from the axis of rotation. And then a force of 84.3 Newton is applied at this end. Maybe we could change the force, actually. Let's make this one perhaps, let's make it 80. Or maybe, I don't know, let's make it 80. Okay, 18 Newton at this point, that is a force, so that we don't get the same number, so you know how to do this one here. This force that we have, let's just say it is 890. The question would be saying, what is the length of the screwdriver? What is the length of the screwdriver? Of what? Of the screwdriver. Now watch this, because the distance for this side is not given, so first you will have to find this distance here. So once again, the torque for this side must equal to the torque at the other side here. Once again, force times distance, you can call it F1, D1, F2, D2. If not, as long as you know which torque's at which side, and that's it. So the force at this side, it is 890 or 890 times the distance of, let's convert this one to meter as well. That is going to be 0.02 meter. That is equal to the force of this side, which is 80, times the distance, which is unknown here. So first you will have to find the distance, which is equal to 890 times 0.02. That's point. Divided by, let's just write this one nicer. Okay, and then divided by 80 Newton. All right, let's get a calculator, see what is this equal to. I got a calculator finally, so what does it say? 890 times 0.02 and then divided by 80. The length we're going to get, all right, this distance, it is equal to 0.2225. So we'll just say 0.22. That is in meter. That is the distance, remember. And of course, you're going to find this answer in one of the choices as well. But once again, that is incorrect. Okay? Why? Because what you found, it is just this distance. In order to find the total distance, you'll have to add this distance, right? Plus, let's just call it distance 1, plus this distance, then of course you'll find the total length of the screwdriver. So at this point here, it is going to be 2 centimeter. How about we convert this one to centimeter, maybe? So 0.22 centimeter, it is going to be 22 centimeter here. So once again, you will see this in the choices, but that is not the length or the total length of the screwdriver. So watch this. This is 2 centimeter for this side. This is 22 centimeter for this side here. So what is the total length for the screwdriver? You'll have to add them together. So you will say 2 centimeter plus 22. So it is going to equal to 24 centimeter. That'll be the total length of the screwdriver, or you can write 0.24 meter as well. So whether given in centimeter or meter, that'll be the total length of the screwdriver. So remember this. This is also another way they could change this question for. All right, see what is next. This is very similar to the question we just skipped, so we're not going to do this one here. But take a look at this one. It says if the torque required to loosen that holds the wheel, this is the same that we just solved with the 56 degrees. This time it is 30 degrees. You could just do that. How about this one here? It says, how would the force needed to open a door change if, let's say, if you put the handle in the middle of the door? Remember, when it says in the middle, that means the distance becomes 1/2. So we know that force and distance are inversely proportional. We said always use this technique, you could say, right? If by whatever the factor the distance is changing, the force must change by the same factor, but they're reciprocal. So if this is the middle, the distance will be 1/2, right? So the force is going to be 2/1, or you could just say the force is going to be doubled, right? Which is going to be option A at this point right here. And regarding this one, we went through this one. Okay, we said, how do we separate rotational and translational motion? We said for those objects that their center is not rotating, we call them a point mass. For those objects that their center is spinning or rotating, we call them extended object. And of course, we went through some examples as well. Next time, inshallah, we're going to start with a rotation and inertia, which is also a very important topic or concept, or you can say one of the main part or important parts of chapter number 2. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.